Adrian Musceac is here again from Romania. And Adrian, I'm glad that you're here again. And you have been here in the past. And but you're a long-time contributor also to this event. And please give a warm applause to Adrian.
Hello. Hello. Thanks for having me here again.
So, this is the last talk for today, and Adrian is going to talk about a DMR base station using GNU Radio and Jonathan Naylor's excellent software, MMDVM. As we have done it in the past, that's a remote talk, and we have pre-recorded the video.
Hello, everyone. My name is Adrian, Yankee Oscar 8, Romeo Zulu Zulu. And today I would like to introduce an implementation of a digital mobile radio base station using MMDVM, GNU Radio, and LimeNET-SDR devices. First of all, about digital mobile radio. It is a land mobile voice and data communication standard created by the European Telecommunication Standards Institute, which implements a double time-slot time division multiple access scheme, also called TDMA. This radio standard can carry two radio conversations simultaneously in a single 12.5 kilohertz channel, which is double the capacity versus an analog FM 12.5 kilohertz channel. This standard also offers caller routing via IP transport between logical channels called talk groups. And because it uses the TDMA access scheme, it requires some strict timing synchronization in order for the mobile station to access the base station, which means that the mobile station only transmits during one time slot window, with the possible other mobile station transmitted in the other time slot served by the base station. Digital mobile radio has recently become quite popular in the amateur radio community and is widely implemented in various countries. And I think software-defined radio implementation of this standard could possibly open some interesting use cases, like, for example, serving multiple DMR channels with one single software-defined radio transceivers, but also perhaps other use cases that somebody might think of. In order to understand the digital mobile radio standard, this slide introduces the DMR frame structure. As you can see in the images on the right side, the base station sourced TDMA frame is comprised of two alternating time slots. Each time slot is 30 milliseconds long, which means about 720 samples at a sample rate of 24 kilosamples per second. The transmission from the base station is continuous. The time slots alternate, and between the time slots there is a common announcement channel being transmitted. And the guard time between each time slot is 2.5 milliseconds, which is relevant for the mobile station originating transmission, pictured in the lower right side of the screen. The received samples need to be aligned in time with the transmitted samples in order to match the time window in order to receive the transmission in the correct time slot. The time base used by the mobile station to synchronize to the base station is set by the base station transceiver. So there is essentially no external time reference required in order for the mobile station to access the base station. In order to implement this digital mobile base station with SDR, there were some software components necessary. And first of all, I would like to know that all used software components are open source, so anybody can actually do this without any restriction. The most important one is, of course, the multimode digital voice modem, or MMDVM, created by Jonathan Naylor. This application, which is actually comprised of two separate components, MMDVM host and MMDVM itself, it supports DMR, D-Star, and EASO System Fusion digital voice standards, and can create a duplex base station. So essentially, somewhat like a normal repeater station. MMDVM implements OSI layers 3, 2, and part of layer 1 of DMR, and it provides to the digital to analog converter, it provides 4-level frequency shifting symbols, which are also filtered with a root-raised cosine filter. MMDVM uses a sample rate of 24,000 samples per second. MMDVM was also designed to run on microcontrollers. Essentially, it requires hardware, external hardware like an FM radio or a frequency shifting transceiver. Most often, the analog devices AD7021 is used in these very specific hardware required to run MMDVM. It communicates with the host application, MMDVM host, using serial port connection. MMDVM was ported to Linux, and it was also modified to connect to MMDVM host using a pseudo TTY instead of a serial port by Peter Rakesh. And I have found this Linux port and then further modified MMDVM to communicate with the GNU Radio flowgraphs using a 0MQ socket, which under the hood use inter-process communication transport to send samples and to receive samples from GNU Radio. Another very important component is, of course, the GNU Radio framework, which I believe everybody is familiar with. It allows us to create dynamically configured flow graphs to digitally process the signals. This framework, in our case, will handle the frequency modulation, the filtering, and the resampling to arbitrary sample rates of the samples provided by MMDVM. This framework provides a mechanism to also create and propagate sample metadata, which are tags associated to samples containing a timestamp, which in our case will prove crucial in order to do the time synchronization required by DMR. GNU Radio communicates with SDR hardware using custom in-tree and out-of-tree modules. In our case, I have used GNU Radio LimeSDR, which is part of the myriad RF libraries supporting LimeSDR devices. GNU Radio, of course, offers a stable API for creating custom C++ blocks in order to do the sample processing, which is what I have used. GNU Radio also allows us to create Python blocks, but in my case, I have used the C++ language to create the processing blocks. Because GNU Radio has a multi-threaded architecture, there is a small but also non-deterministic sample processing latency. And this is important because usually we cannot determine whether there is which exact time our samples will be transmitted by the software-defined radio. So we actually need the crucial mechanism of associating timestamp tags to each sample. The other software components used were QRadioLink, which is an application I have written in order to provide a visual interface for tuning the software-defined transceiver. And this application handles setup of transmit and receive offsets necessary for duplex operation. And it also embeds GNU Radio C++ flowgraphs and can dynamically configure them at runtime. So you can switch modes and toggle transmission on and off and other such configuration. QRadioLink also controls the LimeRFE frontend used for this implementation by providing automatic band switching and setting of the duplex operation. The mechanism used to transmit samples from MMDVM to QRadioLink is 0MQ, which is a messaging queue library which provides sockets to carry messages across various transports like in-process, inter-processing, TCP, multicast communication. 0MQ is asynchronous, so it processes messages asynchronously, and is basically also used by GNU Radio in order to stream samples to other external applications. So you can use 0MQ sources and sinks to communicate between GNU Radio flowgraphs to other external processes. About the hardware I have used, I first started implementing this using the add-on Pluto or Pluto SDR hardware, but unfortunately the Pluto SDR doesn't provide timestamps in the FPGA in order to synchronize the transmission to an exact time. So I have switched to using the LimeSDR family transceiver. And I have tried either the LimeNET-Micro or the LimeSDR Mini. They are both very similar, and they both work pretty much the same. And the most crucial ability is that they can provide FPGA timestamps, which are actually implemented as a sample counter in the FPGA gateway. And this counter is set for each sample packet received. Essentially, we can derive the timestamp due to the fact that we know the exact sample rate the device uses it. So we can convert to seconds and fractional seconds since the start of the receiver. The LimeSDR is capable of duplex operations, so we can set up our duplex base station. And it has software support via the LimeSuite library. I've also used the LimeRFE radio frontend, which was used to provide external filtering and power amplification for amateur radio bands of interest. In my case, it was either the 2-meter band or the 70-centimeter band. This hardware can also operate in duplex mode above 144 megahertz. Is controlled via USB by QRadioLink, which automatically switches to the correct amateur radio band filters and power amplifier, and is also obviously supported by the LimeSuite library. The whole mechanism of, in order to be able to receive the mobile station transmission to our base station, we have to synchronize in time the transmission. So there is a software mechanism of burst time synchronization, which is implemented as follows. When first starting the receiver flow graph, we configure and initialize a local time base, which is then continually updated using the receive time tags provided by the FPGA. These time tags contain seconds and fractional seconds, which are then internally converted into nanoseconds since the start of the flow graph. And this timestamp is also updated anytime the receiver is reconfigured or for some reason the sample flow is interrupted. Using the sample metadata received via 0MQ from MMDVM, we also add transmit time tags inside the custom C++ block for each sample which is starting the time slot burst. This is necessary in order to tell the software-defined radio transceiver at which precise time in the future should start the transmission of the burst. Time tags for each burst need to be far enough in the future to mitigate the GNU Radio flow graph latency, because this latency is not deterministic. So we need to set it far enough in the future that the latency won't affect the time, and the samples will not be dropped by the FPGA. The software-defined radio will then transmit the burst at the exact specified time. Also, we use the tagging mechanism to count the received samples and compare the time of each received sample to the start times of the transmitted bursts, storing the bursts in our memory, and then comparing the time for each sample by multiplying with the known time per sample, because our sample rate is known and is therefore easy to compute the time of the sample. If the timestamp is aligned with the start of a transmitted burst, then sample metadata is added for MMDVM consumption in a custom C++ block to mark the start of the time slot, and then MMDVM will basically process these samples using the metadata and will then receive and demodulate the DMR transmission in the correct time slot. So this mechanism worked fairly well, and I was able to create this base station and be able to receive transmissions from the mobile station, but there are still a couple of issues with this approach, and these issues are actually, I'm currently searching for some mitigations for them in order to improve the code and hopefully minimize them. The issues I have found with this software-defined radio approach, basically using GNU Radio to communicate with the SDR device, first of all, it's the latency of the transmitting and receiving chain. The GNU Radio scheduler and the 0MQ message passing mechanism add latency. So because there are multiple buffers involved and there is message passing involved between the MMDVM application and the QRadioLink application. There is also a minimum latency which occurs because we have to schedule the transmit bursts for transmission in the future. So therefore we have some mandatory latency which is being added, and this latency tends to add up for long transmissions, meaning that we can actually observe the time of the transmission between MMDVM and the actual reception is the time difference is quite large. And another issue which is quite important, but not fatal to our use case, but it is quite important, the base station downlink activation from an idle non-transmitting state to an idle transmitting state can actually take more time than the internal mobile station state machine timers allow for. So the mobile station has an internal timer. The way it operates is it first, in order to access the base station and determine the base station to switch to an active mode, basically transmitting both time slots in order for the mobile station to synchronize to the time base, the mobile station will first transmit an access burst. And then it will switch to receive mode for a determined amount of time, in which mode it will wait for the base station to start its transmission, synchronize to it, and only then it will switch again to transmitting our actual voice to the base station. And it turns out that in our case, the latency of this whole data processing mechanism is a bit more than the mobile station can allow for. So when transmitting the initial activation burst, we sometimes have a missed activation. So the mobile station will not be able to detect in time the base station, and will switch to, it will basically give us an error. Of course, this issue doesn't occur when the base station is already active and transmitting, and then if the mobile station initiates the start of the transmission, it will go over just as fine. However, this issue is mitigated by basically starting the transmission and then waiting for the base station to come up online, and then triggering another transmission, and it will go over just as well. But it is a little bit annoying, and I'm hoping to find some mitigation for this problem. There's also another issue which occurs with MMDVM. It's burst synchronization algorithm, which searches for the sync pattern, is quite sensitive to the receive frequency being offset more than about 100 or 200 hertz from its optimal frequency, which means that thermal drift of the software-defined radio may require tuning of the SDR during operation in order to be able to continue to demodulate the transmission. Of course, this issue can be mitigated by using GPS stabilized oscillator for the software-defined radio, which is one of the reasons why the LimeNET-Micro was an attractive target, because it supports using a GPS DO in order to synchronize the local oscillator and prevent it from drifting. So, of course, all this work would not have been possible without the original work of Jonathan Naylor, G4KLX, which is he's the author of MMDVM and also MMDVM host, and his implementation of DMR, DSTART, and EASO System Fusion is, of course, the thing which enables this software-defined radio implementation. And there is also the work of Peter Rakesh. He's the author of the Linux port of MMDVM, and also the author of the GNU Radio companion flowgraphs, which you can find in his repository of his fork of MMDVM. You can read further information on the website of QRadioLink at the address you can see here. And in the end, I would like to say that this software-defined radio implementation, I don't think it is specific just for digital mobile radio. I think the same mechanism can work just as well with other digital voice standards implemented by MMDVM. So I think maybe DSTAR and EASO System Fusion should also work in pretty much the same way. Except for the fact that I did not have the required equipment to test it. So it's up to the people who have this to maybe test the software and maybe figure out if it works. Anyway, it's been a pleasure to introduce this, and I hope you find this implementation useful in your own projects. Thank you very much.
So, okay. Thank you very much, Adrian, for your contribution. Are there any questions? There's one question.
Hello.
Hello.
Hello. My name's Jonathan Naylor, G4KLX, the author of the MMDVM. I couldn't resist this talk. I find it fascinating the way you did your synchronization. That is the main thing that I thought would be the, how can I put it, the stumbling block for doing this, because the fact that USB connections or whatever are non-deterministic. I love the idea that the tagging of the transmit side. So it's not so much a question as just an appreciation of what you've done. It's that synchronization, I can tell you in the original, did spend a lot of time making that work, the way I did it, of course, which is different from yours. And I know it is a very, very difficult problem indeed. So I think you've done really, really well. I'll try and find your email address and send you an email, and perhaps we can communicate that way.
Yes, of course. I would definitely like to talk to you about this. Originally, I had in mind something like having maybe a single base station hardware which is serving multiple DMR channels. Because you can basically frequency translate multiple channels using GNU Radio, and then have multiple instances of MMDVM and MMDVM host, and be able to increase the capacity, because this is, I think, ultimately for me, this I was thinking mainly of the capacity issue of having many users served on maybe a single repeater cell. So. Yeah, but there could be other applications I haven't thought about.
Indeed, yeah. In fact,
would be nice to discuss this. Yeah.
Yeah, and also maybe Tetra as well, which is something that I was not able to do because of. Yeah.
Originally, this was my initial investigations regarded implementation of Tetra, because so far Osmocom have done a lot of work in implementing the Tetra downlink receiver in both GNU Radio and both in layer 2 and I think part of layer 3. And their code is open source. And of course, going from there to serving a full Tetra 4 timeslot channel, it's merely a case of following the ETSI standard, which is quite big. It's part 2 is 1,000 pages.
Yeah. Well, the DMR is not much smaller, I have to say, but yeah, it's a few hundred. Right, brilliant work, really good. I love it.
Thanks.
All right, thank you. Any more questions? No more questions today. So then, thank you very much, Adrian, for your contribution. Thanks for coming in. Thanks for sharing your ideas.
Thank you.
Please give a warm applause. So, Adrian, so hope to see you again next year.